recording this. Okay, so in continuation to where we stopped with this last time, this slide shows you something. It may not be expected from some of you, which is two conditions. The first one is not, of course, something that we would even think practical, but if you have a journal over here inside a hollow cylinder, which is like a bearing, okay, and the journal is rotating, and as you see, there is nothing inside. There's nothing. It's just air, okay? So whatever is in here is just air. I'm filling it up with some color, but this is just air. Then this is a dry contact, and due to the friction over here, okay, what will happen is with the journal will appear as if it is climbing up the surface of the bearing, so it will tend to stick to that side, okay? And on the other hand, if you fill up the gap with lubricant, okay, against what we think that, you know, probably if you would imagine this in a simple way, you would imagine that the journal is rotating, there is a thin film, and that's it. But the truth is that thin film first indicate that the journal is going to move down and in order to have that thin film. But what is interesting is that due to the rotation and difference in pressure generated by the action of the fluid, motion, and so on, that thin film is actually going to occur over here, right there. So in reality, the journal is going to move down and then a little bit slightly to the left, which means in a general way, this is the line where the journal is going to move. You see that? So this is when we put a lubrication, and for that reason, we will introduce a few terms. The first one is eccentricity. So what we imagine is that the journal is sitting in the middle with its center located here. There is this uniform constant thickness layer, which is the lubricant. Okay, that's the lubricant, ya shabab. And when the journal start to rotate, okay, you will see later that one of the interesting assumptions made to formulate the equation that governs the behavior of the fluid, which is the lubricant, at that little tiny strip, is that the friction between the journal and the fluid, which is governed here by this place, not only this, of course, everywhere. I'm talking about the strip, because everywhere, okay, there is this zero, no slip layer where the fluid will move with the same speed as the journal. But if we focus on this spot, which is the tiny strip, this is fixed and the other one is rotating. It's like the fluid is being pulled and pushed away. Do you understand? And the difference in the pressure is causing the journal to move a little bit to the left side. Okay, so this difference, this is the new center of the journal. Okay, so the difference between the two center, which is, by the way, inclined, is not like this, is E, which is eccentricity. The minimum thickness, as we know, this is the minimum thickness, is H0. The ratio E divided by C is called the, this is repetitive, it's called the eccentricity ratio. I think I put the equation twice. I need to remove it from the other one. And the B, the beta, I mean, is the bearing angular length. Now, if you look down over there, you would see that we have a bushing down, which has an angle beta. So this is only a partial bearing that we will see. So basically, if the bearing shown in the bearing shown in the figure is called or is known as a partial bearing, because this action with the journal, the bearing, and the lubricant in between is happening over the sector indicated by beta. If the radius of the bushing is the same as the radius of the journal, it is known as fitted bearing. If the bushing enclosed the journal, as indicated, okay, by the dash lines, so it covers it all up, then this is called a full bearing. The angle beta describes the angular length of a partial bearing. Like this one, for example, it could be 120 degrees, okay? Now, in order, what are we going to do today is that we will discuss how the governing equation that describe the mechanics of this filament, this little tiny strip, okay, was established by Reynolds. Reynolds, loved mathematics, fluid mechanics, and heat, and so on. So he got the problem and he wanted to describe it mathematically, which what we are going to discuss today. But before he did that, there was a guy whose name is Tower, okay, who conducted an investigation on a partial bearing with beta equals to 157. And as you see what he did, he put on the partial bearing over here, and then the journal is right there, as you see it over here, okay? And then he put on a fluid over here, which is the lubricant. So as you see, the lubricant will touch the journal from below and push around, and this is how the whole thing happens. So what happens is Tower did a lot of investigation, okay? We are in no position here to discuss the detail of how did he conduct his experiment, but he, through experiment, by measuring the pressure through some gauges and so on, he was able to find the distribution of the pressure, okay, along the radial direction and along the longitudinal direction, okay? And Reynolds found the result by Tower, and he understood that, whoa, there is a clear indication that there is this relation. It can be modeled in another way. Okay, so Reynolds said, okay, I am some sort of a geek mathematician and engineer, and I want to establish a relation that governs the behavior. So look, when a guy who is in fluid mechanics and gonna make a mathematical model of some phenomenon, I mean, he will focus on the things that are very relevant. Like if you have a fluid flow, then you would imagine that people would want to know the pressure, right? Maybe friction within the fluid, the viscosity. What about this H0? How much is it? What is it gonna be? Can I know it? If I make a cylinder and then I put a journal and then I put a fluid and I know the diameter of the journal and I know the viscosity of the lubricant and I know the RPM of the, can I predict what is going to be that layer? Is that something I know? Because if that layer is 10 micron or 100 micron or 300 micron, maybe this is going to tell me how much is enough, right? To avoid metal to metal contact. Isn't that nice? So what if the velocity, the RPM decrease? What if the pressure change? What if the viscosity change? Can I have a relation that will guide me, tell me, you know, be careful, if that happened, then this is going to happen. The relation, I can put a number here and get another number. You see that? So that is fancy and nice. And when we speak about it, just like general relativity, right? Everybody likes to talk about Einstein. Everybody likes to talk about time dilatation and curvature of space and Earth and Saturn and Sun and so on. But the math is too much. Yeah, nobody speak about Ricci curvature and whatever, which is like a differential geometry thing, which Einstein used. Nobody. Everybody is speaking only about the curvature, you know, the time, space curve, and that's it. So to do it is too much. You understand? And there is, of course, a lot of boring and sometimes confusing steps that you have to do. So this is what Reynolds did. Now, I want to give you one little hint over here. It is very hard sometimes to teach it the way Reynolds thought about it. Believe me, I probably bet on this, okay? That when Reynolds did this derivation, he did not start with this slide and the one after. He did not. I'm pretty sure. Yeah, he probably made some of these assumptions, but maybe he did something and say, no. Let me try this. Let me try that. So there is a lot of going back and forth. So this picture is a little bit deceiving. You think that it is that way, but it is not. And I will try to explain to you what do I mean later. So there are now two boring slides ahead, too much text, no pictures, and too many things. But please bear with me, just 2 minutes, no more. So first of all, Reynolds imagined in his head that lubricant adhering to both surfaces, which is very reasonable, right? And when it adheres to them, it is being pulled, okay, by the moving surface. And for a geometrical reason, which we are going to explain later, he figured out that I can imagine that there is a surface like this, there is another surface like this, which is being wedged, okay, and the fluid is flowing. Let me put the fluid over here, is flowing here. And of course, this idea of adherence, okay, pulling the fluid to the side. So the fluid is actually flowing, all right, and causing this little tiny filament, okay, pressurized filament, sufficient to prevent this guy from coming in contact with the bottom guy. That's the whole purpose of the journal bearing. Now, one of the important simplifying assumption resulted from Reynolds' realization that the fluid film were so thin in comparison with the bearing radius is that he can ignore the curvature. If you make it too thin, the curvature of this guy is just ridiculous. It's too much. It's almost a straight line. And by making it a straight line, things go so easy. And imagine it, surprisingly, I am almost confident about this, is that if somebody would go and did what Reynolds did today by a computer and assume that the curvature is there, the result will be so negligible in the sense of difference. The difference is going to be so negligible. So you just do a lot of work, but then you get almost the same result. So that's why he made it straight. So the curvature is gone, okay? So he replaced the curvature with a partial bearing as a flat, and a, just a wedge and a flat surface. The lubricant obeys the viscous law. What we said, tau is equal to mu du over dy. You see that this equation will come so handy later. Okay, viscous Newtonian flow. That's it. Okay, and then he said there is no effect of inertia. You know what does that mean? It means that if you sum up the forces and you say this is equals to ma, then if there is no inertial effect, this is gone. This is zero. It's become like a static problem. The fluid is flowing, but he said the inertial effect is too little. I will ignore it. You see that? And then he said that this fluid is incompressible, which makes a lot of sense since we're talking about a lubricant, a liquid lubricant. Liquid, ya shabab, if you take a bottle of water and you want to take the water and compress it, it's incompressible. But if you take air and you want to compress it, yes, it is compressible. So here, we're not talking about an air bearing. We're talking about a lubricated liquid, bearing, okay? He said that the viscosity is constant. Of course, that's a method. Why would you worry about maybe 10 micron the viscosity is this much and another 10 micron the viscosity is a little bit less? You are taking an infinitesimal element. Let's just assume that the viscosity is constant. Of course, these assumptions may not be today, or even after Reynolds published his work, may not be hold accurate, but they are good assumptions. Okay, the pressure does not vary along the axial direction. So what does this mean? If you look at the bearing, if this is the bearing, you see it in this on the slide, the axial direction is along the axle. So at that direction, within the thickness of the bearing may have a thickness this much. So along that thickness, the pressure doesn't change. It's the same. Okay. And that's, of course, makes it easy. We can slice two-dimensional view, because if you slice the one in the back, they are the same. You see that? And then he said that the bushing and the journal extend infinitely in the z direction. This is the z direction. So the depth, we can imagine that this goes forever. This makes it also very simplified, make the problem more simplified. This means that there can be no lubricant flow in the z direction. The film pressure is constant along the y direction. That little tiny H0, okay? Across that H0, the pressure is always the same if you go in the y direction. But if you go in the x direction, as we're going to see, the pressure will change. Why? It makes a lot of sense. If you have it wedged like this and down straight, you can imagine that the pressure here is going to be different than there. But if you look here, along one line in the vertical y direction, the pressure is the same. Now, the velocity of any particle of lubricant in the film depends only on the XY coordinate system. So Z has nothing to do with it. And now let's look, what does this mean? If you, as usual in mathematics, what we do, we look at the whole thing. Okay, and then we say, okay, look what did Reynolds do? He said, okay, here I'm going to assume that this is straight. And in there, I'm going to assume that this is wedged. You see that? So he said, that's why we have the wedging over here. And that's why we have this as a straight or, just a flat plate. That's the first thing. Second thing, this is the Z direction in depth. Nothing there is changing, so we don't care about it. This is the Y direction. and this is the x direction. Okay. Now, what else is this? As you see, h over here is changing with x. So you need always, if you want to know what is x, what is the height at any instant, you need to tell me at what x coordinate you want it, because as we move, h is become smaller. Now, what is the idea here is that if you see this wedge has a velocity equals to capital U, just like what we did in the first lecture. And we said that this one has a zero velocity. It doesn't move. Okay, so this is the velocity of this one is zero. The velocity of this one is capital U. What else? The fluid is flowing in this direction. So it's being pulled and thrown away to the other side. Now, what do we do usually? We say, let's go and take this tiny little infinitesimal element. That element is over here. We call it dy dx. Yeah. And by calling it dy dx, we are indicating that this dy is too tiny, dx is too tiny. Okay. Now, then when we take that element, in reality, we want to draw the free body diagram. We want to take that red element, put it somewhere, and then forget about everything else. Now, once you take it off, you need to apply the boundary condition, right? Now, we want, interestingly, ya shabab, once you do this, you look at it, you get scared. What is b dy dz? What is b dp dx, dx, dy dz, and so on? But don't be scared. I mean, what our main target, honestly, when we do this, is to describe the physics here. Here we have a pressure, right? And we said that pressure along the y direction is the same, but along the x direction is changing. Isn't that right? So ultimately, I want to go back to CE 201 dynamics, whatever, which is what? Summing the forces along x, summing the forces along y, summing the forces along z, summing the moment about a point. This is what we do. So how do we do that? We come here and we look at this. We can, through the relation which says that pressure is equals to F over A, we can say that F equals to PA. Correct? That's it. Everything now is going to come clear. Why? Because all what you need to do now is to tell me what is the pressure, which, by the way, pressure is the same as the stress, right? And so if you tell me what's the pressure or the stress, and you multiply it by the area, I will know the force, period. That's all. And then I will sum up the forces. So what I'm going to do, if you look in here, the pressure at this line, look, ya shabab, this line, the green one, the pressure along the y direction is the same. So let's assume that this pressure is P. Now, if you have a pressure P, you need to multiply it by area to find the force. What is the area? The area is this. Look, it is this multiplied by this. Why? This is dz, because if you do this, look what happened. You get an area. And we get an area. If you apply the pressure acting on that area, you get the force. So instead of writing it F, I am writing it as P multiplied by dy dz. Is that difficult? No. Now, be careful. If we go to this line now, we moved that tiny dx, but because the pressure is changing along the x, then I will have the same area. Look at it, the same area. It is dy dz from the other side right there. That's the area. But the pressure now got higher. So the pressure now is the pressure in here, the green one, plus how much is the gradient? Tell me, how much is the change of the pressure with respect to x? How much? And then multiply it by delta x. That's it. If you tell me the pressure changes 1 megapascal per millimeter, then if I take 1 megapascal per millimeter and I multiply it by 1 millimeter, which is delta x, I will get how much is the increase. So this is the pressure in the green line over here, plus the pressure increase. Yeah, multiplied by the area. Similarly, يا شباب, we know that this is a viscous fluid, and from the relation tau, which is equal to mu du over dv over dy, we know that there is shear forces due to the viscosity. The viscosity is causing the shear stresses. So in reality, if I take that shear stress and I multiply it, be careful. This area now is this one. It is dx by dz. That's the shearing area in here. The pressure area is here and there. The shearing area is down and up. So it is tau by dx dz, nothing, right? If I go up, what did we say last time? We said that if this is moving with velocity u and this is fixed, then the fluid is going to go like that, which means that u will change, which means that tau will change like the mu multiplied by du dy. So as du changes with y, shear stress will change. For that reason, you need to put, I need to clean this now, ya shabab. So for that reason, you need to tell me that how much is the shear stress in here? And by going up, the rate of change, del tau del y, how much is that rate? And then multiply it by this one, dy, which will give you how much that you increased. Yeah? And then you multiply it by this area. That's it. Is this now difficult? No, just a little thinking. Now, when we do this, okay, we can go to our simple friend, summation of forces equals to 0. And where? Along the x direction, because this is where the action is happening. And because we said that there is no inertial effect, we can simply say the summation of the forces in along x direction is not max, it is actually what? 0. Of course, in fluid mechanics, you know what is the density, ya shabab? It's mass over volume, right? So usually in fluid mechanics, it is meaningful to say F is equal to rho V and then A. In that sense, because it has about density and volume. But that doesn't matter. It doesn't matter. We don't need it. It is 0. So look what happened. We take here, just to correct something in this equation, we take the right-hand side as positive, which means this is a positive force. Remember, this is a force. This is a pressure by area, which is a force. It's a force going in this direction against another force going in that direction, which is this one. Sorry, not this one, the other one. Which is this one. And then we have this one over here, which is going in the left, so it is negative. And we have this one positive, which is 3. That's it. That's equals to 0. Now, I am not going to go into too much detail, but this long equation, which seems to be complex, is actually can be simplified to this equation. This is equation number 1, which says that the change in the pressure along the x direction is equal to the rate of change of the shear with respect to y stress, with respect to y. Okay. Now, of course, this is just a differential relation, right? Differential equation. So we need a little help in there. So we realize that by assuming that this is a Newtonian fluid, then tau is equal to mu del u over del y. Now, you may ask a question and say, I mean, how is it going to help if I only replace this with tau equals to mu du over dy? Well, the truth is, switching from stress to viscosity, velocity, and y as a dimension is way more convenient than stress. Stress is not easy to measure, ya shabab, whether you believe it or not. It's not like displacement where you can say, okay, the point is here and then it moved to there, I can know the displacement. So this is making it more convenient. So realizing that this is the equation, we go and plug it in here, and what do we get? We get this, or if we rearrange, we get this differential equation. Now, this differential equation on the left-hand side says the del, the rate of change, the second rate of change of the velocity with respect to the second rate of change, where the second rate of change of velocity with y is 1 over mu dp dx. We can integrate twice, holding x as constant, then we get this relation. Now, this relation, when we integrate it twice, we know that the outcome for indefinite integral is going to be 2 constant. So can we find these 2 constant? Oh, yeah. This is not actually very difficult. Why? Because we know 2 famous boundary conditions. We know that at this line, the velocity u is equals to 0. And we know that on the top, the velocity u is equals to capital U. And we know that at this position, h is equals to 0. And sorry, not h, y is equals to 0. And we know here that y is equals to h. Yeah. So if we do this, if we put at y equals to 0, the velocity equals to 0, we will automatically have this is 0, this is 0, this is 0, so C2 equals to 0. Well, congratulations. There's nothing better than getting the news of a constant being 0, so it's gone. What is the other one? We put u equals to capital U and y equals to h on the top, and then we get C1 equals to this. We go and we substitute C1 back in the equation, and we get what is known as the velocity distribution in the film. So in the film, the velocity distribution is equal to this equation. This is not done yet. We need to, if we can further simplify this. So Reynolds said, how about if we think about the flow rate? The flow rate is how much of the fluid is passing through some area or volume, and that Q, the flow rate, if you integrate from 0, the bottom, to the top, which is h, okay? So this is 0, this is h, u du, then you will substitute the velocity and then define. This is a definite integral. You put y equals to h and then minus y equals to h. Is that right? The 2 limits of the integration. And then that's the trick. Since we assume that this is incompressible fluid, incompressible flow, then actually that means the flow rate change with x is equals to 0. So the flow rate doesn't change with x. And if we do that, this is gonna help us, make the relation much more compact, and then we arrive to this equation. Now look at it. It's the change with respect to x of this, which is h cubed divided by mu, multiplied by the rate of change of the pressure, dp over dx, is equals to 6 times u multiplied by dh over dx. This is called Reynolds equation for one-dimensional flow. Okay, of course, this is not a solution. This is not a closed form solution. This is just a differential relation between the parameter p, x, u, h, and so on. So in that solution, we consider that nothing is changing along the z direction. In another word, there is no leaking. So if leaking is considered, then that equation will grow bigger. Look, it has this another form, which is the rate of change of this part with respect to the z direction. Yeah. Now, of course, this is not going to make it any easier, right? So it is now 12:39. We have only 11 minutes to finish this class. And after a lot of mathematics, I am happy to announce that there is no general solution for Reynolds. So what are we doing here? There's no solution for this equation. Oh yeah, for me, this is more interesting. For you, this is boring and what the hell. So just to tell you that the guy that we talked about before, which is called Sommerfeld, okay, actually his equation was a derivative. This relation, why it is amazing, because it's a general form. It's like it shows you the government of the behavior for the h, the p, the x, the z, the u, and so on. And people, in order to solve this, of course, this is not unsolvable. If it is not solved analytically, this is why we have an entire field, which is called numerical analysis. We solve this numerically by approximation, which is good enough for us. But there are those who try to make some assumptions, okay? Very valid assumption, reasonable and practical, and they were able to deduce simpler relation. Among them is the Sommerfeld equation. Here, I would like to remind you that this is a functional form. So this is phi of this. So there is it's a R over CF is a function of this, which remind you of S, right? Let me try to bring it back here quickly. We said that S is equal to R over C square mu N over P. So this is actually S. Yeah. So the question is this now. If we consider, this is the trick here. If we consider that the assumption that Reynolds made and the mathematics that he derived was accurate, the assumptions, of course, they are assumptions. Then the assumption, I think it is contradiction to say an accurate assumption. It is more, I think it is better to say a reasonable, a justified, a practical assumption. So if we say that Reynolds assumption hold for many practical solutions. And let's say that the simplification that Sommerfeld made are also reasonable. Now look what happened. Look what happened. And now the magic comes. We can look at the equation now and say, okay, as an engineer, I can make decision about the RPM, maybe. Although in reality, most of the time, process specification holds. It's not up to you. They will tell you the process has to go with this RPM, and there is other reasons which you cannot control. But in general, let's say you can have a controlled RPM. In a simple, silly case, you can imagine that the RPM is a dial, and you say, okay, I can make it 1000 RPM instead of 1100. So there you go, guys. This is N. And in a relation, you can see that, oh, the dial is in the equation now. I can play with that equation and then predict what will happen. I know if I increase this, something else will increase. I know if I increase it, something else will decrease. I know I cannot decrease the other thing further. I have a limit here, I have a limit there. This is where the design comes. Look, the pressure, look, the viscosity, the radial clearance, the C, this ratio, the friction. This is wonderful. This is wonderful. So from design point of view, we can group this end of mathematics into two parts. The first one is the independent variables, and it is the viscosity, the pressure, the speed, and the dimensions. Logically, you can make a decision about this as a designer. Now, there are things which are dependent variable, and most of the time, you have no hand on them. For example, friction. Yeah, you can change the viscosity, and it may affect the friction, but to some extent. I mean, and sometimes even you cannot change it. I mean, in the end of the day, friction is not something you can control. It is indirectly controlled. You need to change the viscosity to change the friction. Remember, ya shabab, it's not about making the surface of the journal and the bearings very smooth. You will not get rid of it. It's always there. It's coming from within the fluid itself. You can't. I mean, you can't. The temperature rise. You will always have a temperature rise. It's not up to you. You cannot control something. You say, and there you go. There is no rise in the temperature. Come on, this is not going to happen. You can play with the temperature indirectly by a little bit, but it's not up to you. The oil flow, you can't. I mean, you will end up pushing the fluid with a certain rate to control the temperature, the viscosity, and so on. So you have no control on it. And of course, the etch, the filament, this is natural. This is a law, a physics, a nature. You can't just change it. It's like sunrise. You can't just say, okay, we are going to design housing here, and to avoid overheating in the summer, we're going to switch off the sun. Or we're going to tilt the earth. No. So in summary, we say that A are somewhat under the design or the designer control, while B, okay, are not. So certain limitations should be put on variable B. So B, tell me, I mean, by the way, I like this word limitation very much in design. Why? Because the truth is, designers may think that I own the entire universe. I can make my design, right? From scratch. But the truth is not. Like, for example, when you say, okay, the sky is your limit, what are you going to talk about temperature, huh? From a 0 to 10 million? We know that the fluid, the viscosity, I mean, the integrity of this chemical liquid will be demolished once you reach maybe 300, 400. And we know that you cannot have a lubricant at 1,000. So you are actually limited. So you go and you put limitation on H0, Q, delta T, F, based on experience, standard, and so on. And from there, you can reflect this on what you can control, which is the viscosity, because it's the choice of the fluid, the pressure, which is part of the operation, the RPM, and the dimensions, because you will design the shaft, you may change the size of the journal, and so on. You understand? So, and remember that this idea only comes from a relation, and this relation is right there, and it is a result of Reynolds contribution. In the next class, inshallah, we'll talk about a little bit more consideration for design, okay?